So it's my pleasure to introduce you to Sandipan, who is a PhD student in my group. He's doing so he has done his studies in India, and after he moved to Estonia to Tartu Observatory, where he started his PhD, and he has spent the first 2 years of his PhD in Tartu, working with Michael, me, Anna. And he is supervised by Christiane because we have a complicated arrangement of universities involved here. He's funded through a EU project that's running since 2 years and a bit, and it's a special kind of EU project where you have countries that have a more developed science mentality and infrastructure that help support and foster countries that are still somewhat behind. In this case, we have the UK, Sweden, and us supporting Estonia and the Tartu Observatory. His PhD is at the bridge between stars and planets, and today he's gonna be more towards the stellar side with stellar photospheres and the connection to their planets.
Okay, I guess you can hear me. So the topic of today's seminar is photospheric contamination in early type stars. Photosphere means the atmosphere of the star, and we are specifically looking at that, and we try to connect the abundances that we measure on the atmosphere of those stars with disk. Before we actually start talking about that, just to give you a very brief intro. So most of the stars form in this molecular clouds, quite giant, and at each of these points that you probably see these black dots are the stars where it collapsed. And at each of these points around the star, you have the disk. And behind the star, probably also jet in some cases. And then you have a nice disk around, which is the protoplanetary disk, and you have the star. And then at some point you have the planets, the asteroid belt-like object, and there's one more disk, as in this case, left here. What I'm interested in is between these two stages of planet star and planet formation. And we're just going to a bit more depth into this part. This is a nice picture that I got from Frank Long's webpage. Very colorful. So you have the star in the middle, you have the disk around, and there are lots of processes that happen in the disk. And I think here people know a lot about it anyway. But just to summarize this picture, you have dust, which is around the middle of the disk because they're quite heavy. And then you have gas around them, which is quite light. So you have this big region covered by the gas. And then you have the accretion of material from the disk on the star. So if you look somewhere here, there is no more gas or dust left. Everything sublimates. So what you have is just atoms or even ions, and those accrete onto the star. And what I want to look at is this white ring around that star. So the material which falls from here onto the star, what happens to that? And I just realized today that in the picture there was this question, what are the organic reservoirs? Carbon, nitrogen, and sulfur. Let's see here. One of the elements which is missing here, which is quite interesting, is phosphorus, and which is something I will talk a little bit later, because we don't know much about phosphorus and where they are in the disk. Okay, so just to define how we look at the elements when we measure the abundance, we divide them into two categories. One is volatile elements, another is refractory elements. So any element which you would mostly find in dust, we call them refractory. And any element which is mostly present in gaseous form in the disk, we call them volatile. So for example, carbon or oxygen or nitrogen, they are mostly volatile elements. But for example, if you have iron, magnesium, silicon, calcium, those are mostly in dust. So we divide them into groups. Okay. So this is the whole summary of my work in a way. So you have disk around the stars, and you have the material from the disk which falls on the star. And you can divide them into two parts. One is the gas that falls, and there is the dust that falls. But if you have a planet which formed in the disk, it opens up a gap, which means the gap stops the dust from moving inwards, but gas. So as a result, what happens in these kinds of stars, the full disk or group 2 stars, you have both gas and dust which falls on the star. But in group 1 disks or group 1 stars, you don't have any dust which falls on the star, just the gas. Now, if you look at these stars, and measure the abundances, you would see quite a difference. If you look at, for example, a sun-like star, where you have convection, and convection mixes material from the interior to the outer layers quite well. So you would see any of the accretion that happens from the disk on the star itself, because the convection mixes up pretty rapidly. But if you look at a star which is much hotter than, let's say, 6,500 Kelvin roughly, then you will have a radiative envelope around these stars. If you have radiative envelope, there is not much mixing going on the atmosphere. It's only the rotation of the star which slowly mixes the material with the interior. So when you have this kind of signatures where you have gas accreting on the star but not the dust, what you would see is that the carbon abundance stays the same, whether the material was accreted or not on the star, because both the star and the disk have the same carbon abundance, roughly. But if you have a disk which is depleted in dust, in the inner disk, because the dust was blocked by this giant planet, then you would have iron, magnesium, all the refractory elements depleted when you measure the abundance of dust. Mostly of these stars. These specific stars are also called lambda Bootis-type stars, because that was, I think, the first star in this group, which was known. Just to quickly mention why the planets stop the dust. So when you have an opening of a gap, you have the gas which is still there, but not the dust, because the viscosity that the dust fills, because dusts are quite heavy, so they don't spiral inwards because the gas density here drops, and they just stuck at just the outer region of the gaps. And those dust just pile up as rings around the dust, and that you also see in lots of protoplanetary disks. The opening of gaps, at least here it says it happens because of massive planets, but I guess we're not 100% sure on that. Okay, so that was all good, but what did we observe till now? So one of the early papers on looking at stars with disks, protoplanetary disks, hot stars with protoplanetary disks, was from et al. 2015, also Mexico. There is another work before that by Colin Folsom, who is also our collaborator, who observed a lot of young stars and with protoplanetary disks showing this depletion signature. So what you see here are 5 elements: carbon and oxygen, iron, magnesium, and silicon. And now if you divide these stars into 2 groups, stars with no gaps in their disk and stars with gaps in their disk. So 1 would mean gap, 2 would mean no gap. Then when you measure the stellar abundances, you see that for carbon and oxygen, on an average, the abundances are quite similar. And they're quite close to the solar abundance that you see as well. But if you look at iron, magnesium, or silicon, you see that on an average, they are depleted compared to stars with no gaps in their disk. And the depletion is quite similar in all of the elements. They vary a little, but on an average, they're quite similar. So if we now divide them, so these are the volatile elements that we see. Does not have any variation between the two stars. Gaps are not in the disk. But the refractory elements do show this depletion signature. So one of the questions that we had now was, what would happen if we look at phosphorus? Because we know a bit about phosphorus, but not much. So we know that phosphorus is mostly in gaseous form in ISM, in PO or PN. At least that's what's measured. And then you have phosphorus measurements in asteroids or meteorites in form of different minerals. But we don't know much where the phosphorus lies in that middle stage when you look at these young stars or even planets later. So what we tried to do is do the same plot here, but to include phosphorus. It's quite difficult, but we did something. We can ignore this. Okay. So it's the same plot, same stars as well, but we just used Hubble data. So we had a lot of archival data on Hubble, and specifically this, it's a spectrograph, a UV spectrograph. The thing is, for hot stars, you don't have spectral lines of phosphorus in optical spectrum. And most of the abundance, or all of the abundances that were measured, all of the elements that were measured, are from optical spectrum. And it's relatively easy to do because you have grounded elements. For phosphorus abundance for hot stars, it's quite complicated because then you have to either apply for Hubble data or you have to dig the archive if you can find something. And quite recently, so just last week, I found a few stars which have this archival data. And we see that for phosphorus as well, they seem to be depleted when they are stars group 1 type. So they have gaps in their life. This already indicates that you have phosphorus mostly in refractory form. And this is just a plot, a very rough plot to see these stars, which are like 6 of them, which is not enough to be very confident, but still there. So if you compare the iron abundance of stars with the phosphorus abundance, you see that there is this trend that as the iron depletes, the phosphorus depletes as well. And that tells you that if the dust is not getting accreted, and if phosphorus is in dust, we would expect that phosphorus depletes almost similarly as iron does. And that was something quite interesting because now there are measures or then upper limits on the phosphorus abundance in the disk itself, which I have not shown here because I don't fully understand it. But when we compare that with our measurements of phosphorus on the star, it was quite clear that phosphorus is almost refractory in nature. So they should be found only in dust, not much in gas. And this can be interesting when we look at probably at giant planets and how they're accreting the gas. And maybe we will not find phosphorus in their atmosphere, but I'm not 100% sure. So someone here will know better. Okay, so I have just one equation in this whole presentation. And this equation will repeat itself a few times, but it's a very simple equation. So what I want to tell is, if you have measured the abundance on the star, the abundance is a combination of 2 abundances, actually. You have the abundance of the materials which fall on the star and the abundance of the star itself without any accretion. And you can weight them up with a particular fraction, which we call FPH. So for example, if you have FPH 0, which means there is no accretion on the star because this will be 0, this will be 1. So your observed abundance will be the abundance of the star without any accretion. But if you consider FPH to be 1, then the observed abundance that you measure is the abundance of the accreting material. So everything that you measure from the star is somewhere in between that. You either measure the abundance of the star itself or a combination of the star's abundance and the abundance of the accreting material. But, this fraction itself depends on two things mainly. One is the accretion rate. So how much material is falling on the star? If there is not much material falling on the star, you won't expect much accreting abundance as well. This makes sense. And the second thing is mixing mechanism. So the star also mixes material with its interior. In the interior, it has the same abundance as it had before. It's only the atmosphere where the abundance changes. So if it mixes material from the interior to its exterior, then at some point, this FPH should go down to 0 and you should have the observed abundance come back to the reference abundance as well. The mixing mechanisms are quite different for different kinds of stars. So for hotter stars, you have just the rotation of the star which mixes, and it's quite slow. And for the cooler stars, for example, our sun, you have convection, and that's quite fast. And for sun-like star, if you look at their abundances, we won't expect to see any contamination from the disk because this FPH drops down to 0 quite rapidly as you introduce convection. That's why we look at hotter stars. And for abundances of the star itself without any contamination, there is no way of knowing it from just one star. But if you look at a lot of stars around our sun, we can get a rough abundance estimate of the stars and how they are without any accretion. And we use that as our reference abundance here. Okay, so just to summarize what I have talked till now, is one thing is that the material from the disk accretes on the star. We know that now. We also divided our elements into two groups, volatile and refractory. So elements which are mostly in gas, carbon and oxygen, are volatile. Iron, magnesium, silicon are mostly refractory. And on an average, stars with gaps show refractory depletion. Okay, and so this was the work done till now, and a bit of it I also contributed in the phosphorus, but it's mostly on the stars with protoplanetary disks. But what we wanted to see next is what would happen if you look at stars which have debris disks, but they're quite young. So they just transform from a protoplanetary disk to a debris disk stage. So what do we expect from them? So for that, we looked at a few stars. It's the same slide. I can skip it. Okay. So before that, quickly introducing what debris disks are. So you have planets around the star itself already. You have asteroid-like objects around, and you have a ring of them, which is very similar to what we have in our solar system as well. And then you have asteroids which collide with each other, producing a lot of dust, and in some cases also a lot of gas. So when you look at extrasolar objects, you also see ring-like shapes, for example. Yeah, here are the debris disks that we see. These are not individual asteroids that you see, but just the dust that was emitted as a result of collisions. Okay. So for that, we want to look at the abundances of the stars. So we did stellar spectroscopy using ground-based telescopes in the optical. So it was quite relatively easy thing to do. So we estimated the stellar parameters like temperature, surface gravity, rotation of the star, and other things, and also the abundances. Now, if you plot the abundances very similar to the one plot that I showed for carbon, oxygen, iron, magnesium, and silicon, now we have a lot of elements for which we measure the abundances, so we can look at a lot of things. So here's a plot of different elements. And the circles here represent all the stars in our sample that we observed, or we measured the abundances for. And ignore the yellow stars. And the black star here represents the reference abundance. So this should be abundance of the star without any accretion from the disk. And so if you see any change in the abundance of any of our sample stars, you would know that that's not the star's abundance itself. And if you note, probably along the x-axis, they're not sorted by the increasing order of atomic numbers, but they're sorted by how refractory they are. So, for example, for carbon, nitrogen, oxygen, they would be more volatile. And as you go down the well, they become more and more refractory. So they would be more and more likely to be in dust. And so you see that, for example, for carbon or oxygen, the abundances are quite similar to the reference abundance. But as you go down, for example, for chromium or iron or magnesium, you see that some of the stars have lower abundance than the reference one. Specifically, there are these two stars which show this refractory depletion. So I will come back to this equation again because it's important. Because when you look at the accretion rates for stars with protoplanetary disks, they're quite high. But when you look at debris disks, the accretion rate is quite low. If the accretion rate is low, your FPH is low. So you would expect that these stars have the abundance that we measured to be the abundance of the star itself without any accretion. But we still see the refractory depletion. So we wanted to know why that happens. And this is a very rough plot. The blue dots here show the accretion rates that were measured for stars with protoplanetary disks. And these black dots here represent accretion rates for stars with debris disks. And as you can see, and on the x-axis, you have the age of these stars, and on the y-axis, you have the accretion rates. So you see that the accretion rates drop quite rapidly after around 10 million years. Remember that both of these are log scales, so it's quite rapid. And so after, let's say, around 10 million years, the accretion rates are so low that we wouldn't expect any of the observed abundance to be from disk accretion, because this FPH value goes to 0. So what is suggested is, let's look at the abundances, but in terms of age for different systems. We plotted the age and the iron abundance of the stars, and we use iron as an indicator of all the refractory elements. And for example, we see the same thing as before, that stars with no gaps in their disk show the iron abundance, which is quite similar to their reference abundance, but stars with gaps in their disk so show the iron abundance to be depleted. So the diamond here represents an average value of all of the systems, and circles represent individual stars. The black one here represents our sample of stars, the debris disk hosting stars. And we clearly see that there are two stars which are at a position which is quite similar to this group 1 disks. So here we propose that the red curve that you see here is because around 10 million years, the accretion stopped. And then it's just a star mixing the material from its interior to the exterior. So at some point, it will mix and mix and mix, and your iron abundance will come back again to the reference abundance that you had before. And what we saw in these two stars are at this transition point between the mixing of material, which would mean that the abundances that we measured for these stars are from the materials which are from their protoplanetary disk stage. So we are looking at the past of these stars in a way. There are two stars which are quite interesting for me, actually three stars. So this is HD 100546, which is quite well known, which shows this refractory depletion quite well and very strong. And on a similar level, there is HD 110058, which also shows almost similar level of refractory depletion. And so what we think might be is that at least in the inner disk region, these two stars were quite similar when this star was at the protoplanetary disk stage. And this we need to do a lot of work to actually understand that, but I think that would be the case. This is another interesting star which I have not highlighted, but it's HR 8799, which has like 4 giant planets around. It also has a debris disk, and it also shows this very strong refractory depletion. Okay, so another way to show that the material that we observed for this star's atmosphere is from an earlier protoplanetary disk is by comparing the accretion rates from 2 different ways. Right now, the accretion rate of this star is around 10 to the minus 13 solar masses per year, which is almost zero for all the practical purposes. But we can do it the other way. We have the equation already. We know the observed abundance, we know the reference abundance, so we can get a range of values for what would be the abundance of the accreting material, what would be the FPH that satisfies this equation. And you can do that for different elements, specifically for refractory elements. But the most important part is this figure. So you get a range of accretion rates from this equation. And that accretion rate is around 10 to the minus 7 solar masses per year. And here the black circles I've shown here are the stars with protoplanetary disks around. You see that the population of stars have the accretion rate which is in the same range as the accretion rate I calculated for HD 110058. And this accretion rate, which is 10 to the minus 7 solar masses per year, is quite high compared to the accretion rate that we actually measure for this star. So it gives more support to the idea that probably the abundance that we measured for this star is from the materials which was accreted from the protoplanetary disk stage of the stars. Now, if we look at instead of volatile abundances, we do not expect to see any change. So for example, if you look at the carbon abundance with age, you see that the carbon abundances between the protoplanetary disks and between the protoplanetary disk and the debris disks is quite similar. So there is not much of a change. Okay, so we see a tiny change here, but probably it's not significant enough. I'm not sure. But if you look at the oxygen abundance, specifically in the younger systems, you see that there is this downward trend of oxygen abundance with age. And here I removed all the error bars for it's kind of cheating, but it's okay. You know there are error bars here, both in the Y direction and the X direction, both quite big. But if you still are convinced that there is a downward trend, then we need to ask the question why that happens. And we see that this downward trend there is not much of a difference whether you look at group 1 or group 2 stars, or you look at young debris stars. There is this oxygen depleting over time. Now, if the oxygen abundance that you measure for the star is the oxygen abundance of the depleting material, then what you're looking at is that the oxygen abundance in the inner disk itself is depleting over time. And there are some observations, I think, where the water in the inner disk is depleted over time in cooler stars. Yeah, but we don't exactly know. Just to show you some other work which was done on this. For some reason, all the references. But this is from Ma et al. 2024. We looked at the disk itself and to look at the inner disk specifically and the evolution of different things. So, for example, the water, how it evolves with time in the inner disk, or the oxygen abundance, or the CO2 ratio, or the carbon abundance itself. Just focus here for now. So, so in the x-axis, they consider that they have a disk around the star. They have a gap in the disk, and that gap has different strengths of how much they can block the dust from moving inwards. So the third regime, which is this big portion of the image, is the disk where the gap is very strong, so it does not let any of the dust to move inwards. And the 2 and 1 are then the gaps which let some of the dust to move inwards and all of the dust to move inwards. And along the y-axis, you see the evolution. So it's the time. And we are not sure the oxygen abundance trend that we saw in our case for stars, where they fit, because this is a 2D plot. But you can still see a clear trend that with age, the oxygen abundance does get depleted in the inner disk. And so we might expect to see that in our stars as well. And there are different explanations of why that happens. So in the case of disks with very strong gaps, the dust have ices around them. And if the gaps formed, let's say, beyond the ice line, then the water will also be trapped in the dust in the ring around the gap, and you won't find any water in the inner disk. So with time, we do expect to see this depletion of oxygen abundance in the inner disk as well. There are different explanations for other stuff as well, which I don't exactly understand, but I think it would be interesting to look what that happens. Also, there was this recent paper by Long et al. 2025, and it's on a completely different type of star. They are M-dwarfs, the coolest stars, I think. So they calculated the CO2 ratio in these stars as well. And I think some of it, or at least one of the stars, was also contributed by Charity. They looked at the CO2 ratio with age for these stars, and they found one of the oldest protoplanetary disks around, M-dwarf. 30 million years is quite old. And they see that the CO2 ratio kind of looks like it's increasing with time. And if the oxygen is getting depleted with time, you would expect the CO2 ratio to go up. I don't know why that happens exactly, but there are different ideas that are thrown around, but maybe someone else knows better. What I tried to do is, if we have the carbon abundance and the oxygen abundance already measured, then we can just, for the stars, then we can just overplot on this plot as well, our own data. And this blue and red circles again represent group 1 and group 2 stars, and the black one represents the debris stars. And this box represents this M-dwarf stars. And it does that the CO2 is going up with time. We don't exactly know why. That's something we want to work on. But it would be interesting to see why that happens. And yeah. Okay, I think I am almost at the end, or at the end. So I will conclude my talk. So one of the things that we looked at is phosphorus is mostly in dust. We know something about which minerals they should be in, but it's still, I guess, a work in progress. We also know that A-type stars, the young ones, do show contamination from their earliest disk, protoplanetary disk. We also see the depletion in oxygen with age, but we need to think how we can extend it. And one thing that I skipped in the whole presentation is A-type stars, but they're quite old, hundreds of millions of years old, and they still show refractory depletion, and we don't know why that happens. There are some ideas of why that can happen. If the giant planet formed quite early in the disk, then a lot of material, the spore material was accreted on the star. And then you have even the interior of the star, which is refracted. And that might explain the old A-type star populations as well. I will end my talk with something quite different from what I talked about. It's a picture, which I really like, and I saw yesterday. It's, I think, quite beautiful. It's about a spiral galaxy, gravitationally lensed pi-spiral galaxy that was observed by James Webb just a week ago. I think it's quite cool that we can see even the stars here. So, yeah. Okay, so I'll leave with my conclusions again, and thank you.
You're always faster than everybody.
Start with the younger ones.
Go ahead.
Oh yeah, so very nice talk. So is it recorded or? So my question is, you assume that if there's a gap opening planet, it will stop the migration of dust. But according to the simulations, that doesn't happen. Yeah, so dust reaches the fragmentation barrier and then it converts into small dust, which is coupled with the gas, and it is transported across the barrier just like gas, yeah, because it's coupled. So is this an assumption that you make that the dust is not transported at all, or is there some evidence, or how does your results change if like it's actually transported with the same abundance ratio? So that's the question.
Okay, so at least for the phosphorus case, what I found is that they were able to get the upper limit on the phosphorus abundance in the gas, and we measured the abundance on the star. They don't match, so the phosphorus abundance on the star is slightly higher than the upper limit that we get for the gas itself. So
compared to the disk, or?
Yeah, compared to the disk gas abundance, the phosphorus abundance is slightly higher on the star itself. So what we think happening is that some of the smaller dust grains is also accreting with the gas as well, but not all of the dust.
Okay. But maybe just a quick question: is there direct evidence that about the transport? Because I know only simulation results. So.
Yes. There is evidence for cooler stars that calcium abundance does get depleted for the same type, if there are gaps in the disk or not, and that's directly measured from the accretion view, so like an emission line. So I would think it's from the gap.
So I have a comment and then I have a question. My comment is, maybe you don't know that, but only a year ago we had two scientists here, Till Käufer and Jayati Kanwar, who were actually analyzing these ÖAW thank you. Observations of these, what they call VMLS, so very low mass stars, VLMS, yeah. And they found actually spectroscopically sometimes evidence for even much higher C/O ratios, not only 2 or 3, what you showed. And so I think this is actually a nice connection somehow between your work and the work previously done here in this group. I just wanted to point that out. And the question is, when you go back in your slide, you had this work from long. So the CO as function of time or of age. I think it was one of your last. Yes. Do you know, is that some observational spectroscopic constraint, or where does this point come from?
I'm not very confident, but they say that they model to get C2 ratio in the inner disk. But how they modeled it exactly, I don't know. But I don't think.
But is it some kind of hydro model? No, it's probably some kind of spectroscopic model. Yeah. So a disk model or whatever. Yeah. So. Because the interesting thing, that is something that you didn't mention. So for these very low mass stars, why do they show this high carbon to oxygen ratios? And the idea is that the disk evolution actually happens faster. So because, say, you would scale that with the orbital time, in the inner disk of these very low mass stars, it's just absolutely tiny. So you can imagine that the disk evolution, which lasts for a certain absolute time, is faster intrinsically. And so it goes actually into this regime, which most of the T-Tauri stars don't get to before they lose the mass. So you need these low mass stars in order to have the kind of utmost effect of disk evolution on that. So you should see, when you have that now spectroscopically in your stars, but I think you can't do that for M stars. Huh? No, because I was about to say you should see a clear trend with the stellar type, but
I have two questions. The first one is about the abundances. How are they derived? Like from observation, right? Because you saw when you show that some elements they have 10 to the minus 8 ratio with respect to hydrogen, if I'm correct. And I'm wondering how the error bar are derived. I think it was in the beginning when you had all the different stars you were showing.
Yeah.
With something of 10 to the minus. Here 10 to the minus 6, 10 to the minus 8. This means that the spectral feature of so you divide a very small number, and I think the error bar would be pretty big. So I'm wondering, can you comment on this?
So, for example, barium is quite low, but the spectral line can be still quite strong. If they're hot stars, for example, they can have populations in a transition where they still show quite a strong absorption line, even if the abundances are low. Okay. So you can still fit the data quite well, even if the abundances are low.
Okay, I see. Okay. And the second question was you had this graph where you showed the group 1 and 2, the two different populations. So you have a reference abundance, and it was not where the stars were, and I was wondering why. Here or the next one is even more. Here. Yeah. I would say, especially the bottom panel, the reference is completely off the population you measure, or not off, but within. It's even more pronounced than the trend you are trying to discuss. What the offset is, and can you comment on this?
I can comment that I don't know exactly, but I know that the reference abundance is quite difficult to measure because we measure it just from the population of stars around the sun. So the actual reference could be actually somewhere up top. I don't exactly know why that happens.
I mean, to comment on that point, as far as I know, the early evolution is actually you expect to find an oxygen enrichment in the inner disk because you have pebbles coming in and they actually liberate the water that they have taken from the outer disk, and therefore you start with an overabundance of oxygen, and then as it evolves, you might end up with a depletion of oxygen.
I have a question. Thank you, first of all, for this very nice talk. I have a question to the second last slide, or to the third last slide. Oh, that's it. This one.
Yeah, this one.
See it?
But so we see a trend, but what happens at 3 million years?
Yeah, yeah.
I mean, it seems to be for the M-type disks and for your disks, right?
Yeah. I would say they are just 2 data points. Because at least for stellar abundance, carbon and oxygen are a bit difficult to measure well enough, and there can be, for example, non-LTE effects as well, which can actually change the abundance a bit. And these abundances are taken from different references. Not all of the abundances are from me.
Okay.
I will blame them for. If it's real, then it's interesting. So, yeah, I was also thinking about it, but I'm not sure.
But these are all derived from stellar spectra.
Yes,
Points.
circles, yeah.
The circles, whereas the others?
And the green ones are.
Okay,
I just overplotted.
nice.
But this means your circuits have all the same methods for deriving the stellar spectra, right? So then you're quite okay.
Yeah. If it's real, then that would be amazing. I don't know.
Okay.
Also, one more thing, age uncertainties are quite big, so they might move somewhere
okay.
around.
Do you have an idea how big it is?
3, 2
What is?
million years.
Oh, then you're big. No, well, then you're sitting up there.
It's still somewhere here.
Yeah.
If it moves here, then maybe it will be solved. Yeah.
More questions? I take this opportunity to actually point out that this month we actually have 2 more talks in a colloquium that can be linked to actually Sandipan's talk. So the 10th of April, so next week, we have a colloquium on the demographics and structure of protoplanetary disks. I got from the University of Grenoble. And on the 24th of April, so Thursday there, we have Maria Bergermann, an expert from the research group leader from the MPA Heidelberg, and her talk is about chemical composition of galactic stars in 3D and non-LTE. So she will talk about the variation of element abundances within the galaxy, which might be relevant for the reference data he's using on top, T effects. So, and with this, I would like to all thank.
No, I had one comment on, because you have several fittings with a lot of points with error bars. Maybe also you have a lot of points in like low age and only few points later. And I think there are methods to fit statistically with the error bar, with the distribution of the weight at different, like, because you can imagine if you have 10 points here and 1 point here, they should be weighted properly because, so anyway, and that might give you a stronger argument to claim trends. Also with confidence percent, whatever. So there are methods for this. They even package for that. So you can look into it. I think it's in general for everyone.
But still, let's thank Sandipan again for basically providing a good. I hope it's here all next week. Anyway, after. Jag sage det. Ganz extra andere auf. Ihr habt ja auch nicht ausgehabt. Anyway.